Hello everyone, today in this video we'll be discussing about the topic quantum mechanics. So in the module 2 we have mainly 4 topics which are important from the exam point of view, and the whole module is related to a few derivations and theoretical concepts which include about light and about electrons and protons. So we'll be discussing all the important questions which you need to know from the exam point of view. So if you watch this video till the end, it will be enough for you to score more than 80% of the marks. So make sure you watch this video till the end, and if you like this video, hit the like button, subscribe to my channel for more videos like this. So without wasting any more time, let's get started. So our first topic is the de Broglie hypothesis. Okay, so what is the de Broglie hypothesis? So as we know that the light is having a dual nature. That means it is having particle nature as well as the wave nature. Okay. Sometimes when it is observed that in the different scenarios, the light behaves as a particle nature, showing the properties of particles like electrons and neutrons and all. Okay. And sometimes it shows the wave nature, which is in the form of waves. Okay. So that is the difference between the particle nature and wave nature. And since light has both of them, it is called as dual nature of light. Okay. And since the everything in the nature seems to be symmetrical, so what happens is the assumption which is made is light and the other particles of matter, which include every other matter which is apart from light, right? All those things also have two types of natures, and this is also observed scientifically and experimentally. So we go with that assumption. Okay. So dual nature of matter means that the particles also behave in two different forms, in the particle form and the wave form, and that includes electrons, protons, neutrons, and other particles. So the waves associated with the moving particles is called as matter wave. Okay, here we have the light wave, here we have the matter wave. Okay, so this is called as de Broglie's hypothesis. So de Broglie proposed that as light has dual nature, the other particles also has dual nature. Okay, so proceeding with this hypothesis, what all we get to know is that what are the matter waves characteristics. Okay, so the first one is that the wavelength lambda of de Broglie wave with a particle mass m and velocity v, that is given by lambda is equal to h by mv. Okay, this is mass into velocity, and matter waves are not electromagnetic waves, and the amplitude depends on probability of finding the particle. This concept is very important, we'll be discussing in the upcoming topics. It has also a derivation of probability density, and the speed depends on the mass and the velocity. Okay, so let's have a look at some of the important derivations. The first one is the de Broglie's wavelength. So in all these derivations we are trying to calculate lambda. Okay, we are trying to calculate the wavelength lambda. So let's have a look. According to the Einstein's energy equation, we have E is equal to mc square. Okay, and also according to the Planck's quantum theory, we have E is equal to h nu, where nu is the frequency. Therefore, mc square is equal to h nu, and nu can be written as c by lambda. Okay, so mc square is equal to hc by lambda. In that way, we can calculate what is lambda. Lambda is equal to h by mv, because c is equal to the speed of light, so it can be written as v here. Okay, so that is how you represent the de Broglie's wavelength, h by mv. This is the standard equation. Now, there are other ways also to represent it. One of the important ways is in terms of kinetic energy. How can we represent the wavelength in the terms of energy? Okay, so E is equal to half mv square, the kinetic energy. So let's take P is equal to momentum, which is mv. So what this will become is, if we take mv here, we have to take the denominator m in the here, so that it cancels out and turns out to be the same here. So it will become p square by 2m. Okay, so from there we can calculate what is p. If we shift 2m to here, we will be getting p is equal to root of 2me. Okay, this is the expression for the de Broglie wavelength um, by using p. Okay, now we will be using p to calculate the de Broglie's wavelength. So as we know, lambda is equal to h by mv. Here we have mv as p, so it will become h by p, and the p's value is 2me, root 2me, as we calculated here. Okay, so the lambda in the terms of energy, it can be written as h by square root of 2me. Okay, the third one is de Broglie's wavelength of an accelerated electron. Okay, so for accelerated electron, we consider a situation where there is an electron charge E, and in a potential V. Okay, so EV is equal to half mv square. Okay, so this is the potential energy, this is the kinetic energy, both will be equal. So EV is equal to half mv square. If P is the momentum of the electron, then P is equal to mv, right? So squaring both the sides in this equation, P is equal to mv, so we will get P square is equal to m square into V square. Okay, so after rearranging the terms, what we get is mv square is equal to P square by m. Okay, and mv square we can substitute. Where we can substitute? Half mv square, right? So EV is equal to, instead of half mv square, what we will be writing is P square by m. Okay, so we will be getting P is equal to root of mev. Okay, next we have the according to de Broglie, lambda is equal to h by P, and here we have lambda is equal to h by root 2 me. So by substituting the value of root mev, what we get is this value. Okay, and the h is the Planck's constant. We'll be writing 6.26 into 10 power minus 34, and we'll be getting this value. Okay, this is in terms of potential V, okay, of an accelerated electron. Okay, these are the three very important derivations which you need to know from the exam point of view. Next we have phase velocity and group velocity. What is phase velocity? So whenever electron is traveling in the direction, it will be having a wave property, right? So this is the wave which is given here, and this is the x direction. Okay, so in this wave, as you can see, there is a high peak which is shown as P, and here it is P dash. Okay, so this single wave is there, right? So what is the velocity of that wave? That is called as the phase velocity, and it is given by W by K. Okay, W is the frequency and K is the constant. If multiple such waves travel together, it is called as wave packet. Okay, that wave packet has a velocity which is called as the group velocity, and that is denoted as dW by dk, differentiation of frequency with respect to K. Okay, that was about the first topic, de Broglie's wavelength. Moving on, we have a very important concept from exam point of view, Heisenberg's uncertainty principle. Okay, so what does Heisenberg's uncertainty principle state? It is impossible to measure both the position and the momentum of a particle accurately. Okay, suppose that an electron is moving. Okay, so it will have some speed, right? That speed will be having a momentum. If we want to predict what is the momentum of it, we cannot predict what is the position where it is at the particular point of time. And if you try to predict where it is at the point of time, we cannot know for sure what is the momentum. Okay, this is observed experimentally. So there are uncertainties present here. If delta x and delta px are the uncertainties in the position and the momentum, then the total uncertainties product will be given as delta x into delta px, which is greater than or equal to h by 4 pi. Okay, this is the Heisenberg's uncertainty principle equation. Okay, now where do we use the uncertainty principle? A very important concept in the proving the non-existence of electron in the atomic molecule. Okay, so how do we start it? So first thing, we know that energy of a particle is given by half mv square, that is equal to P square by 2m. Okay, and applying the Heisenberg's uncertainty principle, which is delta x into delta px is greater than or equal to h by 4 pi. The diameter of the nucleus, as we know, it is in the order of 10 power minus 14 meter. Okay, so this is the diameter of the nucleus, and if the electron is to exist inside the nucleus, so if it's existing inside the nucleus, then delta x should be less than this value, right? Obviously, because if it is existing, the value cannot be greater than this one, because it should exist within the diameter. So delta x value we have got here. Now to calculate the momentum's uncertainty, we will be putting the value of delta x in the equation, Heisenberg's uncertainty principle. So when we put this value, we'll get a value of 0.527 into 10 power minus 20 kg meter per second. Okay, and by considering a minimum uncertainty in the momentum of the electrons, it should be greater than or equal to this value, right? Minimum uncertainty should be greater than this. Then the equation 1 will become E is equal to P square by 2m, which is the energy equation. That if we substitute the value of P and 2m here, we have obtained the value of m in the first equation and a value of P in the second equation. So if we substitute those values, we will get the value of mass of electron, which is 9.11 into 10 power minus 31 kg. Okay, so this is the mass we have got. Now what we are trying to prove, the non-existence of electron inside the atom, right? So if the electron exists inside the nucleus, then the energy must be greater than or equal to 9.11 into 10 power minus 31. This is the minimum value we are considering, right? Since we consider the minimum momentum here. So this value of the mass is minimum mass. So if it has to exist, it should be greater than or equal to this value, that is equivalent of 95.68 MeV. Okay. It is experimentally observed that the electron's energy in the beta decay is 3 or 4 MeV. See, it is 3 or 4 only, but here we are required to have at least 95. So what does that indicate? It indicates that the electron does not exist inside the nucleus. Okay, so this is a very important concept, the application of Heisenberg's uncertainty principle in the non-existence of electron in the atomic molecule. Okay. Next, we have the principle of complementarity. What is complement? Complement means if two things add up together and form a better version, like 2 plus 2, that is equal to 4. So this is complementing this. Okay, like that. Okay. So in here also we have the two things which are complementing each other, which is the particle nature and the wave nature. Okay. So the particle nature and the wave nature are complementing each other. When the particle is observed, when the particle nature is observed, the wave nature is not observed. Okay, and vice versa. So when the wave nature is seen, the particle nature is not seen. Okay. So general question comes in the mind that how both momentum and the particle's position cannot be observed accurately. What happens when we try to do so? Okay. So when it is tried experimentally, what happens is the following. Okay. So in this graph, as you can see, there is a wave given here. Okay, this is called as a wave, and the x-axis is this one, and the y-axis is here. Okay, so the wavelength is nothing but the length of the complete wave from the top to bottom. Okay, like this, starting till the end. What is the wave? This red line indicates the length of the wave. Okay, so the wave length is certain here. We have all obviously got to know the wavelength. But what is the position? By wavelength we can calculate momentum. So momentum is certain here. What is the position of the electron? The position of the electron can be anywhere in the x-axis from 0 to infinity. So as you can see, such a big uncertainty is there in the position, while we have the 100% certain wavelength. So this shows that when we try to achieve 100% accuracy in the wavelength, the electron's position becomes uncertain, because see, the whole wavelength is uniform and we don't know which part of the wavelength has the electron present, that position. Okay. Similarly, if we try to do the other one, if we try to first calculate the position accurately and then try to see what is the momentum, at that time what happens is, suppose that we get the position of an electron within this range. Okay, but what happens is we get a varying amount of wavelengths. See, as you can see, these are the derivations. These three images are the derivations of the last image. Okay, so here different kinds of wavelengths are seen. So wavelength certainty is very down. Okay, if position is 100%, the wavelength is 0% certain, right? So that's why we cannot observe both momentum and the particle's position at the same time. Okay, this is how the results vary when we try to achieve accuracy in one of them. Okay, next we have the wave function. What is a wave function? So since the particle moves in the waveform, the function which describes the particle in the physical state is called as a wave function, and it's given by this symbol here. Okay, that is a e power I kx minus wt. Okay, this is coordinates equation. And next we have the probability density, that is nothing but the wave equation square. Okay, so if this is the wave function, then the wave function square is nothing but the probability of finding that particle. So suppose that, for example, if there is a volume tau, okay, and the probability of finding the particle inside this space is nothing but wave function square into d tau. Okay, it is a probability of the particle existing in the volume tau. Okay, so probability density is used to find whether the particle exists or does not exist. What is the probability of it? Okay, by using the square of wave function. Next we have very important question from exam point of view, Max Born interpretation of wave function. So what does Max Born say is that the A which is present here, it is called as amplitude, that is means it is the intensity of the wave, how intense the wave is. Okay, and it is obtained as follows, wave function into wave function's excited state, that is A square, where A is the square of the amplitude. Okay, that's all you need to write in the Max Born's interpretation of wave function. Next we have normalization and expectation. Okay, now since we have got equation where we are trying to find out if the electron exists or not, normalization and expectation set some value to it. Okay, for example, the probability of finding a particle in a finite volume tau, that is equal to uh, wave function square into d tau. This is the probability of finding the electron or the particle inside that space, inside the space tau. Okay, so here we have 0 to tau, the limits we have from 0 to tau it should be, and finding that particle is equal to 1 because we are assuming that the particle is present inside that space. Okay, if the particle exists outside the volume, then the limits will be turned from 0 to tau to, it will turn from minus infinity to plus infinity, and still it will be 1 because the particle exists, we are telling. In case that it is not equal to 1, it involves a constant. Okay, this is all you need to know. These three main points are there, and this whole process is called as normalization. The function is called as normalized wave functions, and the value of function is called as normalization factor. Okay, if there are a range of different values, okay, this we are considering a single constant value. If there are a range of values, then that is represented as E. Okay, E, and this range is called as expectation value. Here we represent as x, which is minus infinity to infinity, wave function square into dx. Okay, so this is the range of expected values where it can exist. Okay, moving to the third topic, very important question: time independent Schrodinger wave equation. Pay attention to this one. This is a step by step way you can remember this one to derive the Schrodinger wave equation. Okay, so it can be asked for 8 marks in the exam. So first consider a particle m moving with the velocity v. Okay, there is a particle m, it's moving with the velocity v. Okay, and the de Broglie wavelength is lambda. Okay, so lambda is given by h by mv, that is equal to h by p, we already know. Also the wave equation, as we had discussed earlier, it is a e power I kx minus wt. Okay, now we are differentiating this equation with respect to time. The second equation we are differentiating with respect to t twice. Okay, so what we get, d square w by dt square is equal to minus a w square e power I kx minus wt. Okay, so this equation minus a e power I kx wt, this can be given as this symbol here, right, the wave function. So this is substituted as wave function, and this one minus w square remains as such. Okay, this equation will be taken as 3. Now the equation of a traveling wave. Okay, a wave which is traveling, that equation is given in the terms of displacement and velocity. So dy by dx, d square y by dx square is equal to 1 by v square d square y by dt square. Okay, similarly for the de Broglie also we can represent the same, just change y to the w of the wave function, and we obtain this following here. Okay, now what we are trying to do, we are trying to from the equations 3 and 4 we are trying to derive something. This is equation 3 and this is sorry, this is equation 3 and this is equation 4. Okay, what you can observe here, this term is common. Okay, this term is common in both, right? Sorry, not this is t. Okay, so this term is common in both here. So what we can equate is this term and this term we can equate, right? So when we equate both of these term, what we obtain, sorry, we are trying to substitute this part here. Okay, d square y by dt square. Okay, d square y by dt square, what it is, d square y by dt square is equal to this one, because y is equal to the wave function. So this value we are substituting in the place of this. Okay, this value we are putting here. Okay, so what we obtain, we obtain d square w by dx square is equal to 1 by v square minus w into wave function square. Okay, and two values we know, w is equal to 2 pi into nu, and v is equal to nu into lambda. Okay, when we substitute these both values in the given equation here, we obtain 1 by lambda square is equal to minus 1 by 4 pi square w d square w by dx square. Okay, this is the equation we obtained for 1 by lambda square. Now we are trying to substitute 1 by lambda in some other place. Okay, so which is that place? Kinetic energy is given by half mv square, that is equal to p square by 2m. Okay, so also kinetic energy is equal to h square by 2m lambda square. Okay, and here we have, here we are using the equation 5. Equation 5 is this one. Okay, now we are trying to substitute this one in the place of 1 by lambda square. 1 by lambda square is present where? It is present here. Okay, so in the place of this we'll substitute this value, this whole value. Okay, so when you do that, what we'll get is h square by 2m. Okay, h square by 2m into this whole equation. Okay, and then simplifying it, we will be obtaining this equation here. Okay, this is in terms of kinetic energy. Now observe carefully. We have total energy is equal to kinetic energy plus potential energy. Okay, so E is equal to minus h square by 8 pi square m into w. Okay, and into d square w by dx square. This is taken from here. The kinetic energy plus potential energy is nothing but v. Okay, now rearranging the terms, we have to obtain an equation in the form of this. Okay, so we'll get this one is equal to this value here, and when we shift this value to here, we'll be getting the d square w by dx square plus 8 pi square mw by h square into E minus v is equal to 0. This is the main equation we'll be using for other derivations as well. Thus coordinates time independent equation. Okay, and they can also ask you for the three-dimensional case. All you have to do is a small edit here. What is present here, it is present as x here, right? So you have to put here as y, and z also you have to add, and here we have the E minus v, and nothing is there after that, but here we have to add w of x, y, and z. Okay, these are the two additions you will have to put. Okay, three terms here and three equations here. Okay, that's all about the time independent coordinate wave equation, and we'll be using this equation to calculate what is the particle's energy in an infinite potential well. Okay, so here what we have is the following figure. Okay, observe carefully. There's a well. Okay, and that well's limits are x is equal to 0 to x is equal to a. From 0 to a the well is present, and the particle is present inside this well, and the potential is going on increasing to infinite in the y-axis, and inside this well the v value is 0. Okay, and the particle is present inside well which is having a v value 0, and outside the well, which is outside means greater than a, in these values, in all these places there is v as infinite. Okay, so there are two things: v is equal to 0 inside the well where a particle is present, and outside the well v is equal to infinite. Okay, now in the well x is equal to 0 to x is equal to a, the v is equal to 0, the potential is 0. Outside the well v is equal to infinite, the potential is infinite there. Okay, now the Schrodinger's equation outside the well. We are considering Schrodinger's equation in two places. One is inside the well and outside the well. So outside the well, the v value is infinite, right? So this will become as infinite is equal to 0. And the Schrodinger's equation inside the well it is v value is 0. So here we'll be taking it as 0. So we'll be getting E into W. So for simplicity, we'll be taking this term here, 8 pi 8 pi square m by h square. This whole term will be taking as k square. Okay, and then the equation will become as d square w by dx square plus k square by k square into w is equal to 0. Okay, so the solution of above equation is that w is equal to c cos. This is the equation we are considering. Okay, this mathematically derived equation, we need not worry about that. We have to just learn how it is. So w is equal to c cos kx plus d sin kx. Okay, just remember kx here and c cos d sin. Okay, now we are considering it at 2 points. When x is equal to 0, the w value is equal to 0. So substitute k is equal to x is equal to 0 here, and w is equal to 0. So what we obtain here, we obtain 0 is equal to c cos 0 plus d sin 0. That is equal to nothing but c is equal to 0. Next we are trying to see x is equal to a. When x is equal to a, the w is equal to 0. Okay, because at both the points when x is equal to 0 and x is equal to a, the wave equation will become 0. Okay, so 0 is equal to c cos ka plus d sin ka. Okay, but c is equal to 0 from the above equation, so we obtain d sin ka is equal to 0, but d also cannot be 0. If both c and d become 0, then the wave equation vanishes, so d cannot be 0, therefore sin k is equal to 0. If sin k is equal to 0, k into a is equal to 0, or any other term n pi, because sine any multiple of pi, that will be equal to 0. Sine pi is 0, sine 360 is 0, sine 540 is 0, and so on. Okay, so n's value can be 0, 1, 2, 3, and so on. So k value will be written as k is equal to n pi by a. Okay, where a is a constant. The limit which we are trying to put in the well, right? So x is equal to 0 to a. Okay, so that a we are taking it here. Now substituting equation 5 and 6 in 4, we obtain this value is equal to d into sine n pi by a x. Okay, this is a very important equation. So from where we are substituting this value, we have here as the equation 3 where it is. Okay, this is the equation 3, right? Here. So here we are substituting the value of 4, 5 and 6 in equation 4. Okay, here we are substituting in equation 4, we are substituting the value. Since this is 0, we are taking this value. W is equal to d sine kx, and k value is n pi by a, so it will become d sine n pi by a, x is equal to w. Okay, so that value we have taken here. Okay, this is the called as permitted wave functions. Okay, so the energy eigenvalue is given by substituting equation 6 in 3. Okay, so where we had 8 pi square by h square, we are considered k, right? So now k value we know, so we are substituting the k value and simplifying this equation. So what we obtain is E is equal to n square h square by 8 ma square. Okay, so rearranging this value now. Since n value is there, n cannot be 0. N cannot be 0 because it would mean that the electron is not present in the well. If n is 0, n should be greater than or equal to 1. Okay, now we have to find the value of d. Okay, this is another equation. To find the value of d, what we are going to do is we are considering this equation. A is equal to means the integral of 0 to a, and w square probability density of dx is equal to 1. Okay, this is the equation we had got previously. Now what we are trying to do, we are trying to substitute the value of w square dx, that is nothing but d square sine square n pi by a, because w value is, what is the w value? D square sorry, d sine n pi by a into x. This is the value of w, right? So w square will become the square of this, and then applying the trigonometric formulas which are given here, like converting the sine theta into cos theta and then separating it and finding the integral, we obtain an equation for the d which is root 2 by a. Okay, so we know that w is equal to d sine pi by a into x, n pi by a into x. So d sub value substitute here. This is the official equation. Okay, next we have the eigenvalues and the eigen functions. So the eigen functions have the following properties: they are single valued, finite everywhere, and they are continuous. Okay, so if the wave function is operated by a quantum mechanical operator, okay, so this is a quantum mechanical operator. If it's operated by a quantum mechanical operator and we get back the multiplied wave function, the multiplier is called the eigenvalue. Okay, so if it is operated by a quantum mechanical operator, it will multiply the value of eigen function. That multiplier is called as the eigenvalue. Okay, now we are going to consider the energy of particle in different states in the well. Okay, like n is equal to 1, 2, 3, like that. Okay, so first value is n is equal to 1, which is the ground state, the starting state. Okay, so substituting the value of n is equal to 1 in this equation, will obtain as n pi, n will become 1, so it will become pi by a. Okay, now the w1 is equal to 0 for x is equal to 0 and x is equal to a, means when the value of x is 0 and value of x is a, the value of the equation is 0. Okay, why is it? Because see, in x is equal to 0, this is the wave function. Here it is pointing at the bottommost, and here also it is pointing at the bottommost. That means the value of this is 0. Y is equal to 0 at both this point and this point, right? So y is nothing but this one here, so this one's value is 0 in both these points, and it's maximum at the middle, which is a by 2. Okay, so it is maximum when it is a by 2. Okay, next we have the second state. Before that, the energy of a particle at the ground state is equal to h square by 8 ma. Okay, that's all. H square by 8 ma, normal, because the value of n is 1 here, and will be substituting 1 in this place, so we'll be getting h square by 8 ma. When n is equal to 2, what happens is it will become n square, right? So here it is 8 ma, this will become as 4 ma, means 4 times the energy of this equation. So how does that happen? See here. Here we have the pi 2 w2 as root 2 by a sine 2 pi by a into x. Okay, and this is value is 0 for x is equal to 0, a by 2, and a. For 3 values it is 0. Okay, means at this point, at this point, at this point, y is 0, y is nothing but this. So this is 0 at the 3 points here, and it is maximum when a by 4 and 3 by 4. Okay, when we take the square, it will become positive here, so it is 2 place maximum, and the equation will be energy equation will be 4 times e. Okay, because n is equal to 2, n square will be equal to 4, so 4 times of e naught it will become. Okay, Next we have the n is equal to 3. In the second excited state, we'll substitute the value of n is 3 here, and we get the following places where it is 0, and we take the square. We will get the 3 maximum places, which is a by 6, a by 2, and 5a by 6. And the energy will be E3 is equal to 9 E naught. Okay, 9 times E naught. So these are the most important questions, enough for you to score more than 80% marks in the exam. So if you like this video, hit the like button and subscribe to my channel for more videos like this. And thank you so much for watching. I'll see you in the next one.